Welcome to Tech with Kaushik. This is set 20 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 20. Here comes question number 356. This one focuses on S3 auditing. An application processes highly sensitive files stored in a dedicated Amazon S3 bucket. The compliance department requires an unalterable audit log capturing every single object-level API call made against this bucket. Crucially, the logs must also capture unauthorized access attempts, such as GetObject calls that are explicitly denied due to invalid or missing IAM credentials. Which logging mechanism will fulfill these exact requirements? The choices are: Option A, create an AWS CloudTrail trail in the account. Enable S3 data events logging specifically for the target bucket. Deliver the trail logs to a separate, secured S3 bucket or Amazon CloudWatch logs. Option B, enable Amazon S3 server access logging on the target bucket. Configure the target for the access logs to be a separate S3 bucket in a different AWS account. Option C, enable AWS config and add the S3 bucket level public access prohibited managed rule. Route configuration changes to an Amazon Simple Notification Service, Amazon SNS, topic. Option D, configure Amazon Guard Duty and enable S3 protection. Create an Amazon Event Bridge rule to capture all S3 findings and log them to Amazon CloudWatch logs. In this case, choose Option A. Create an AWS CloudTrail trail in the account. Enable S3 data events logging specifically for the target bucket. Deliver the trail logs to a separate, secured S3 bucket or Amazon CloudWatch logs. This works because AWS CloudTrail is the authoritative service for logging API activity. By default, CloudTrail only logs management events. To capture object-level S3 API calls, like GetObject, PutObject, DeleteObject, you must explicitly enable S3 data events. Crucially, CloudTrail captures the identity context and logs API authorization failures, such as requests rejected due to invalid IAM credentials, immediately, satisfying the compliance requirement. B. Amazon S3 server access logging provides a best effort log of requests for billing and traffic analysis. However, it does not guarantee delivery, and it is less reliable for capturing API requests that are rejected early in the IAM authentication phase compared to CloudTrail. C. AWS Config is a configuration evaluation tool. The S3 bucket level public access prohibited rule checks if public access blocks are enabled. It does not log individual object-level API calls. D. Amazon Guard Duty detects threats and anomalies, like unusual access patterns. It does not provide a raw, unalterable audit log of every single API call made against the bucket. A helpful shortcut is this. If an audit requirement mandates recording all object-level API activity on an S3 bucket, including unauthorized/rejected attempts, always select AWS CloudTrail S3 data events over S3 server access logs. Next, question number 357. Scenario. A company forwards application logs to an Amazon CloudWatch logs log group. During a recent audit, the security team discovered that sensitive employee IDs, formatted consistently as YMPXXXXXX, where X is a digit, are being written to the logs in plain text. Engineers frequently query these logs using CloudWatch Logs Insights. To comply with privacy policies, the DevOps engineer must ensure that the employee IDs are masked automatically when viewed by engineers, while retaining the underlying log structure. Which solution achieves this with the least operational overhead? Choices. Option A. Create a data protection policy for the CloudWatch Logs log group. Define a custom data identifier using the regex pattern EMP-D6. Ensure the engineer's IAM policies contain a deny statement for the logs. Unmask permission. Option B. Create an AWS Lambda function that parses incoming log lines. Uses regex to replace EMP-D6 with asterisks, and writes the scrubbed logs to a new log group. Give the engineers access only to the new log group. Option C. Configure an Amazon Kinesis Data Firehose subscription filter on the log group. Route the data through an AWS Lambda transformation that obfuscates the IDs, and output the data to an Amazon S3 bucket for the engineers to query via Athena. Option D. Attach a resource-based IAM policy directly to the CloudWatch log group. Add a condition block that specifies AWS principal tag /role equals engineer and apply an obfuscate string transformation function to the emp-d6 string. Go with Option A. Create a data protection policy for the CloudWatch logs log group. Define a custom data identifier using the regex pattern emp-d6. Ensure the engineer's IAM policies contain a deny statement for the logs. Unmask permission. Let's look at the reasoning. Amazon CloudWatch Logs offers native data protection policies that use machine learning and pattern matching to identify and mask sensitive data in transit. By creating a custom data identifier using the provided regex, emp-d6, CloudWatch will automatically mask the data with asterisks when users query the logs. The original payload is securely retained. By denying the logs unmask IAM permission, you ensure the engineers cannot bypass the masking when querying via CloudWatch Logs insights, satisfying requirements with zero custom compute. Let's quickly check the incorrect choices. B. Creating a Lambda function to parse, scrub, and duplicate log data into a secondary log group introduces significant latency, doubles storage costs, and adds operational overhead to maintain custom regex parsing code. C. Routing logs through Kinesis Data Firehose to S3 requires managing a complex streaming architecture, maintaining transformation lambdas, and forces the engineers to change their workflow from CloudWatch Insights to Athena. D. CloudWatch log groups do not support resource-based policies with arbitrary transformation functions like obfuscate string. Data protection policies are the correct native feature. Exam tip. To mask sensitive data in Amazon CloudWatch Logs without writing custom code or duplicating data, implement CloudWatch Logs data protection policies and control visibility using the logs. Unmask IAM permission. Question number 358. We're moving on to enforcing encryption. Here's what is happening. A financial services firm operates many member accounts in AWS organizations. A regulatory policy requires direct S3 put object requests made by identities in these member accounts to use HTTPS and to explicitly request server-side encryption with AWS KMS keys, SSEKMS. The DevOps engineer needs an organization-level preventative guardrail that rejects a direct upload request if transport is insecure or if the request omits SSEKMS or requests SSES3. Which mechanism will enforce these requirements proactively across the member accounts? Review the options. Choice A. Attach an SCP to the organization root with deny statements for S3. Put object when AWS secure transport is false and when the requested server-side encryption is absent or is not AWS KMS. Choice B. Deploy an AWS config conformance pack that checks S3 default encryption and deletes non-compliant objects after they are created. Choice C. Configure Amazon May-C to discover non-compliant objects and invoke a Lambda function that rewrites them with SSEKMS. Choice D. Create event bridge rules for S3 put object activity and invoke a Lambda function that deletes uploads that do not meet the encryption requirements. The right response is Option A. Attach an SCP to the organization root with deny statements for S3. Put object when AWS secure transport is false and when the requested server-side encryption is absent or is not AWS KMS. The main reason is an SCP is a preventative permission guardrail for IAM identities in member accounts. A deny on AWS secure transport equals false rejects non-TLS requests, while a deny for a missing or non-AWS KMS S3 server-side encryption request rejects uploads that do not explicitly request SSEKMS. The request fails before the object is created. The other choices do not work because B. AWS config evaluates configuration after the fact and does not prevent the put object request. C. May-C discovers sensitive data and findings after data exists. It is not an inline S3 upload control. D. Event Bridge and Lambda are reactive after API activity rather than a preventative authorization guardrail. The main takeaway is S3 encrypts new uploads by default with SSES3, but a compliance rule that requires explicit SSEK-MS and HTTPS needs authorization conditions for both at-rest method and secure transport. Question number 359. An organization relies on an Amazon Aurora PostgreSQL database for both transactional data loading and complex analytical queries. Recently, data analysts reported severe slowdowns. Upon investigation, a database administrator discovered a long-running idle transaction that was blocking system vacuum processes. The team wants an automated solution that will proactively monitor the database for these specific operational anomalies, identify the root cause, and send actionable recommendations to the database team via Amazon SNS. Which AWS solution satisfies these requirements natively? Option A. Enable Amazon RDS performance insights on the Aurora PostgreSQL cluster. Enable Amazon DevOps Guru for the account and configure it to monitor the Aurora resources. Configure DevOps Guru to emit notifications to an SNS topic. Option B. Enable Amazon RDS enhanced monitoring with a granularity of 1 second. Create an AWS Lambda function that parses the enhanced monitoring CloudWatch logs to detect idle transactions and publishes alerts to an SNS topic. Option C. Create an Amazon Event Bridge rule that matches Aurora database configuration change events. Route the events to AWS Trusted Advisor to generate optimization recommendations and forward them to an SNS topic. Option D. Deploy the AWS distro for OpenTelemetry, ADOT, sidecar alongside the database cluster. Export custom PostgreSQL metrics to Amazon Managed Service for Prometheus, AMP. Create a PromQL Alert Manager rule to notify SNS. The answer here is Option A. Enable Amazon RDS performance insights on the Aurora PostgreSQL cluster. Enable Amazon DevOps Guru for the account and configure it to monitor the Aurora resources. Configure DevOps Guru to emit notifications to an SNS topic. This is the best choice because Amazon DevOps Guru is an ML-powered service that natively detects operational issues in AWS environments. When Amazon RDS Performance Insights is enabled, DevOps Guru for RDS can deeply analyze database telemetry to identify complex performance anomalies, such as idle transactions blocking vacuum operations, resource contention, and locking issues. DevOps Guru automatically generates actionable recommendations and can natively route these findings to Amazon SNS for proactive alerting, completely eliminating the need for custom alerting logic. Here's why the alternatives are not suitable. B. Amazon RDS Enhanced Monitoring provides deep OS-level metrics, but writing a custom Lambda function to parse raw CloudWatch logs to detect database transaction locks is complex, error-prone, and carries high operational overhead. C. AWS Trusted Advisor provides broad best practice checks, like unattached EBS volumes or open security groups. It does not perform real-time ML analysis on database performance metrics to detect transient transaction locks. D. While ADOT and Prometheus can collect database metrics, building custom PromQL queries to detect complex blocking behavior and generating recommendations requires significant expertise and operational effort compared to the managed DevOps Guru service. Here's a useful exam tip. Amazon DevOps Guru for RDS relies on Amazon RDS Performance Insights to automatically detect database performance anomalies, like blocking transactions, and provide remediation recommendations. Question number 360. Let's go. The focus now shifts to region guardrails and monitoring. Scenario. A government contractor uses AWS organizations to manage multiple AWS accounts. Due to strict data sovereignty regulations, the contractor must enforce two policies: preventatively block the provisioning of any AWS resources outside of the United States regions, for example, US, East, 1, US, West 2. Generate an immediate alert if any user or process attempts to perform AWS API actions in a non-US region, ensuring new or enabled regions are automatically covered. Which combination of actions will meet these requirements? Choose 2. Identify all valid responses. Options. Option A. Attach a service control policy, SCP, to the organization root with a deny statement for all actions where the AWS requested region condition does not match the allowed US regions. Include exceptions for global services. Option B. configure an organization-wide AWS Trail delivering logs to Amazon CloudWatch logs. Create a CloudWatch metric filter matching events in non-US regions, and configure an alarm on this metric to send an alert. Option C. Attach an IAM permissions boundary to all IAM roles using AWS CloudFormation stack sets. Configure the boundary to allow actions only where the AWS requested region condition matches the allowed US regions. Option D. Use Amazon Event Bridge to trigger an AWS Lambda function every 15 minutes. Configure the Lambda function to iterate through all active AWS regions via the EC2 Describe Regions API, detect deployed resources, and send an alert if non-US resources are found. E. Enable AWS Security Hub across the organization. Activate the SIS AWS Foundation's benchmark standard and rely on the native check that validates all resources are deployed in the primary operating region. You should choose option A. Attach a service control policy, SCP, to the organization root with a deny statement for all actions where the AWS requested region condition does not match the allowed US regions. Include exceptions for global services, and option B. Configure an organization-wide AWS Trail delivering logs to Amazon CloudWatch logs. Create a CloudWatch metric filter matching events in non-US regions, and configure an alarm on this metric to send an alert. The scenario requires both a preventative block and a detective alert. The Service Control Policy, SCP, using the AWS requested region condition with a deny effect provides the preventative block, ensuring no API actions can provision resources outside the allowed US regions. Exceptions are required for global services, like IAM or CloudFront, to function. Delivering an organization-wide CloudTrail to CloudWatch logs allows the use of metric filters. By filtering for API events where the region is not a US region, a CloudWatch alarm can immediately trigger an SNS alert if an attempt occurs, providing the requested detective control automatically for any newly enabled regions. The remaining options can be eliminated because C. IAM permissions boundaries must be attached to individual roles. They do not prevent the root user or a user without the boundary attached from operating outside the allowed regions. Managing this via stack sets is prone to configuration drift compared to a global SCP. D. Polling all regions with a custom Lambda function is a slow, reactive anti-pattern. Furthermore, it only detects resources after they have been successfully provisioned, violating the requirement to preventatively block provisioning. E. A AWS Security Hub provides compliance checks, but relying on a benchmark check is a reactive mechanism that evaluates resource configuration post-deployment. It does not provide real-time alerts on API attempts. To restrict an AWS organization to specific regions, apply an SCP denying actions where AWS requested region does not match the allowed list. Always include exceptions for global services like IAM**, CloudFront**, Route 53**. Next, question number 361. A media processing application runs on a fleet of Amazon EC2 instances managed by an Amazon EC2 auto-scaling group behind an application load balancer, ALB. Recently, memory leaks in the application caused several instances to stop processing requests. However, the auto-scaling group did not terminate these unresponsive instances, and they continued to receive traffic until an engineer manually restarted the service. The operations team requires the infrastructure to automatically terminate and replace instances that stop responding to application requests. Furthermore, the team must receive an immediate alert if this health check configuration is ever modified. Which solution meets these requirements with the most operational efficiency? Option A. Configure the auto-scaling group to use ELB health checks. Activate AWS config. Create a custom AWS Lambda function to check auto-scaling group configurations. Set up an Amazon Event Bridge rule to invoke the Lambda function daily and send an Amazon Simple Notification Service, Amazon SNS, alert if a change is detected. Option B. Configure the auto-scaling group to use EC2 health checks. Set up an Amazon CloudWatch synthetic canary to validate the application endpoints. Create a CloudWatch alarm that triggers if the canary fails and configures an auto-scaling action to replace the instance. Send an Amazon Simple Notification Service, Amazon SNS, alert when the alarm triggers. Option C. Configure the auto-scaling group to use ELB health checks. Activate AWS config. Deploy an AWS config managed rule to verify that auto-scaling groups use ELB health checks. Create an Amazon Simple Notification Service, Amazon SNS, topic for the operations team and configure the AWS config rule to publish compliance change notifications to the topic. Option D. Configure the auto-scaling group to use EC2 health checks. Create an Amazon CloudWatch synthetic canary to test the application. Create a CloudWatch alarm to trigger if the canary detects failures, and configure the alarm to publish a message to an Amazon Simple Notification Service, Amazon SNS, topic for the operations team. The best choice is option C. Configure the auto-scaling group to use ELB health checks. Activate AWS config. Deploy an AWS config managed rule to verify that auto-scaling groups use ELB health checks. Create an Amazon Simple Notification Service, Amazon SNS, topic for the operations team and configure the AWS config rule to publish compliance change notifications to the topic. Here's why. By default, an auto-scaling group uses EC2 status checks, which only verify instance hardware and network reachability. By configuring the auto-scaling group to use ELB health checks, the group will automatically terminate and replace instances that fail the ALB's application-level health checks. AWS config provides a managed rule, auto-scaling group HELB health check required, that continuously monitors this setting and can send SNS notifications if the configuration drifts. Now let's rule out the other options. A. While this uses ELB health checks, creating a custom Lambda function and scheduling it daily introduces unnecessary operational overhead and does not provide near real-time detection compared to native AWS config-managed rules. B. EC2 health checks will not detect application-level memory leaks. Using a synthetic canary adds complexity when the ALB health check can directly inform the auto-scaling group. D. EC2 health checks are insufficient for application-level monitoring, and this option does not automatically replace the instances or monitor for configuration drift. Keep this point in mind for the exam. Whenever you have instances behind an ALB that hang or fail at the application level but are not replaced, the first step is to switch the auto-scaling group from EC2 health checks to ELB health checks. Question number 362. This question takes us into CI/CD pipelines. A DevOps engineer is configuring a continuous integration pipeline using AWS code pipeline. The source code is hosted on GitHub, and the pipeline uses an AWS Code Connections connection to integrate with the repository. The pipeline has a source stage that successfully triggers on new commits, followed by a build stage using AWS Code Build. The build stage includes a script that must execute a full Git clone to retrieve Git submodules using the same Code Connections connection. The source stage functions correctly, but the build stage consistently fails with an access denied error during the clone operation. What is the root cause of the build stage failure? Options. Option A. The AWS CodeStar connection credentials have expired or were rotated in GitHub. Option B. The AWS Code Build service role lacks the necessary IAM permissions to use the Code Connections connection. Option C. The Code Build project must be configured to use a GitHub Personal Access Token, PAT, instead of the Code Connections connection. Option D. The AWS Code Pipeline service role lacks the CodeStar connections. Use connection permission. In this case, choose option B. The AWS Code Build service role lacks the necessary IAM permissions to use the Code Connections connection. This works because when a code pipeline source stage uses an AWS Code Connections, formerly CodeStar Connections, resource, the code pipeline service role requires permission to use it. However, if an AWS Code Build project explicitly needs to interact with the repository, such as running Git clone for submodules or deep history, the Code Build service role itself must also have the CodeStar connections. Use connection IAM permission to authenticate against the connection. A. If the connection credentials were bad, the source stage and code pipeline would also fail to fetch the source artifact. C. Code Build fully supports using the Code Connections connection resource natively. Reverting to a PAT defeats the security and centralization benefits of the connection. D. If the code pipeline service role lacked permission, the failure would occur in the source stage, not during the execution of the Code Build script. A helpful shortcut is this. Every AWS service that directly interacts with a shared resource requires explicitly granted IAM permissions. If code build executes Git commands relying on a connection, its specific service role must allow use connection. Question number 363. Let's go. Scenario. A data analytics platform provides a read-only web UI through Amazon CloudFront. CloudFront routes requests to an application load balancer, ALB, and an Amazon EC2 auto-scaling group with a desired capacity of 3. The application uses a pre-built AMI and instances become ready in about 1 minute. The application queries data from an Amazon OpenSearch service domain. The company must implement disaster recovery in a secondary AWS region. The design must minimize ongoing disaster recovery compute cost while targeting an RTO and RPO of less than 30 minutes. An ALB is already provisioned in the disaster recovery region, and the disaster recovery endpoint must be able to serve traffic immediately when CloudFront fails over. Which solution best meets these requirements? Choices. Option A. Create a new CloudFront distribution for the disaster recovery region and use Amazon Route 53 failover routing. Copy the AMI to the disaster recovery region. Create an auto-scaling group with a desired capacity of 3. Configure OpenSearch service multi-availability zone with standby and place the standby nodes in the disaster recovery region. Option B. Add the disaster recovery ALB as the secondary origin in the existing CloudFront distribution and configure an origin group for failover. Copy the AMI to the disaster recovery region and create a launch template. Create an auto-scaling group with a minimum and desired capacity of 1 and a maximum capacity of 3. Deploy a second OpenSearch service domain in the disaster recovery region and configure cross-cluster replication from the primary domain. Option C. Create a new CloudFront distribution for the disaster recovery region and use Route 53 latency-based routing. Copy the AMI to the disaster recovery region and create a launch template. Create an auto-scaling group with a desired capacity of 0. Deploy a second OpenSearch service domain in the disaster recovery region and configure cross-cluster replication from the primary domain. Option D. Add the disaster recovery ALB as the secondary origin in the existing CloudFront distribution and configure an origin group for failover. Copy the AMI to the disaster recovery region. Create an auto-scaling group with a desired capacity of 3. Configure OpenSearch service multi-availability zone with standby and place the standby nodes in the disaster recovery region. Go with option B. Add the disaster recovery ALB as the secondary origin in the existing CloudFront distribution and configure an origin group for failover. Copy the AMI to the disaster recovery region and create a launch template. Create an auto-scaling group with a minimum and desired capacity of 1 and a maximum capacity of 3. Deploy a second OpenSearch service domain in the disaster recovery region and configure cross-cluster replication from the primary domain. Let's look at the reasoning. Option B provides a reduced but functional warm standby. Keeping one EC2 instance running means the disaster recovery LB has a healthy target when CloudFront origin failover occurs, while the auto-scaling group can scale toward production capacity after failover. OpenSearch service cross-cluster replication maintains a second domain in the disaster recovery region for cross-region recovery. This meets the recovery objective without paying for the full 3-instance compute fleet continuously. Let's quickly check the incorrect choices. A. OpenSearch service multi-availability zone with standby provides high availability within a region. Standby nodes are not placed in another region. Running the full EC2 fleet in disaster recovery also costs more than necessary. C. An auto-scaling group with desired capacity 0 has no instances to serve traffic. Without a separate mechanism that raises desired capacity during failover, the secondary ALB is not immediately usable. D. OpenSearch service multi-availability zone with standby does not place standby nodes in another region, and maintaining 3 EC2 instances in disaster recovery does not minimize ongoing compute cost. Exam tip. A pilot-like compute tier with desired capacity 0 needs an explicit recovery action to scale it up. If the failover endpoint itself must already be usable, keep a reduced warm standby capacity and scale out after failover. Now for question number 364. Next, let's move into CloudWatch metrics. Consider this situation. A large enterprise operates hundreds of microservices within a single AWS account. Each microservice is configured to send its application logs to a distinct Amazon CloudWatch logs log group. Recently, the monthly billing statement indicated a substantial increase in CloudWatch logs ingestion costs. A DevOps engineer has been tasked with quickly identifying the specific microservices, log groups, responsible for the surge in ingested log data. Which approach provides this information with the least operational overhead? Option A. Use AWS CloudTrail to filter create log stream and put log events API calls and aggregate the data volume by application over the billing period. Option B. Navigate to Amazon Cloud Watch Logs Insights and execute a cross-log group query counting the number of distinct log streams updated in the last 7 days. Option C. Generate a cost and usage report in AWS Cost Explorer filtered by the CloudWatch service to review the overall account-level logging costs. Option D. Use Amazon CloudWatch metrics to query the incoming bytes metric across all log groups and use metric math to rank the groups by data volume. The best choice is option D. Use Amazon CloudWatch metrics to query the incoming bytes metric across all log groups and use metric math to rank the groups by data volume. The main reason is Amazon CloudWatch Logs automatically publishes metrics to the AWS/logs namespace. The incoming bytes metric directly represents the volume of uncompressed log data ingested by each individual log group. By querying this metric and using a metric math expression, like sort, a DevOps engineer can instantly identify which log groups, and therefore which microservices, are ingesting the most data, meeting the requirement with the least overhead. The other choices do not work because A. CloudTrail logs API calls. Put log events is a high-volume API call, and analyzing CloudTrail data for log payloads is both prohibitively expensive and highly complex, introducing massive operational overhead. B. Counting the number of log streams via Logs Insights does not accurately measure the data volume, bytes, being ingested, which is the driver for the cost. C. Unless all log groups are strictly tagged and cost allocation tags are active, AWS Cost Explorer will only show aggregate CloudWatch Logs ingestion costs for the entire account, not the breakdown per log group. The main takeaway is to monitor or troubleshoot CloudWatch Logs ingestion rates and costs at a granular level without custom tagging. Always look at the incoming bytes metric in the AWS/logs namespace. Question number 365. Let's go. A company manages its application deployments through an AWS code pipeline CI/CD workflow. The development team wants to integrate an automated load testing suite to validate performance under stress before code reaches production. The pipeline must deploy to production only if the load tests verify that latency remains below a defined threshold. A DevOps engineer must design this integration to minimize infrastructure management and operational overhead. Which solution satisfies these constraints? Options. Option A. Provision Amazon EC2 instances to run the load testing tools. Use AWS step functions to orchestrate the test sequence within code pipeline. Use an Amazon Event Bridge rule to invoke an AWS Lambda function that evaluates the test results and returns a success or failure status back to code pipeline. Option B. Create an AWS code build project configured to run the load testing tools. Add a code build test stage in the pipeline to execute the load test. Use Amazon CloudWatch alarms to monitor latency metrics during the test. Integrate an AWS Lambda function into the pipeline via a custom action to check the alarm state and dictate whether the pipeline proceeds. Option C. Deploy the testing tools alongside the application using AWS Elastic Beanstalk. Trigger the tests natively during the Elastic Beanstalk deployment phase. Use an AWS Lambda function to monitor Elastic Beanstalk environment metrics and fail the code pipeline deployment if the latency threshold is breached. Option D. Use Amazon ECS with AWS Fargate to execute the load test containers. Write an AWS Lambda function to trigger the Fargate tasks, analyze the output logs, and integrate it with code pipeline via a custom action. The Lambda function will evaluate the latency threshold and return a success or failure state to the pipeline. The right response is option B. Create an AWS code build project configured to run the load testing tools. Add a code build test stage in the pipeline to execute the load test. Use Amazon CloudWatch alarms to monitor latency metrics during the test. Integrate an AWS Lambda function into the pipeline via a custom action to check the alarm state and dictate whether the pipeline proceeds. This is the best choice because AWS Code Build is a fully managed build service that natively integrates into AWS code pipeline as a test stage, eliminating the need to manage underlying compute infrastructure like EC2 or custom Fargate orchestration. By generating load with Code Build and monitoring the application's response using CloudWatch alarms, the pipeline can leverage a Lambda custom action to accurately read the alarm state and either fail the stage or allow promotion to production. This provides the most robust, serverless integration with the least management overhead. Here's why the alternatives are not suitable. A. Managing EC2 instances just to run load tests introduces significant operational overhead for patching, scaling, and lifecycle management. C. Elastic Beanstalk is an application deployment service, not a testing orchestration tool. Bundling load testing tools into the application deployment payload violates separation of concerns and complicates the deployment package. D. While Fargate is serverless, orchestrating the tasks manually via a Lambda custom action requires writing and maintaining complex custom polling and state tracking code. Code Build is explicitly designed to handle managed task execution within code pipeline. Here's a useful exam tip. For running automated test scripts, including load generators like JMeter or Taurus, inside a pipeline, AWS Code Build is typically the lowest overhead native solution because it handles compute provisioning, logging, and state tracking automatically. Next up is question number 366. This question takes us into high availability. Here's the scenario. A company's financial application currently writes transaction records to a single-node Amazon RDS for Postgres QLDB instance. During a recent availability zone outage, the application experienced significant downtime because the database was unreachable. A DevOps engineer has been instructed to update the architecture to ensure the database remains highly available and recovers automatically in the event of hardware failure or an availability zone outage. Which action will fulfill this requirement? Here are the options. Choice A. Migrate the database to Amazon DynamoDB global tables to ensure active writes across regions. Choice B. Modify the Amazon RDS-DB instance to operate as a multi-availability zone deployment to enable automatic failover to a synchronous standby. Choice C. Deploy an application load balancer in front of multiple Amazon RDS read replicas distributed across several availability zones. Choice D. Migrate the workload to Amazon EC2 instances spread across multiple availability zones, backed by a single Amazon Elastic Block Store, Amazon EBS, multi-attach volume. The answer here is option B. Modify the Amazon RDS-DB instance to operate as a multi-availability zone deployment to enable automatic failover to a synchronous standby. Amazon RDS multi-availability zone deployments provide high availability and failover support for DB instances. RDS automatically provisions and maintains a synchronous standby replica in a different availability zone. In the event of an infrastructure failure or availability zone disruption, Amazon RDS performs an automatic failover to the standby so that database operations can resume quickly without manual intervention. The remaining options can be eliminated because A. Migrating from a relational SQL database to a NoSQL database, DynamoDB, requires complete application rewrites and schema redesign, which is beyond the scope of a simple high-availability upgrade for an RDS workload. C. Read replicas provide read scalability, but do not provide automated failover for write operations. Additionally, ALBs are for HTTP/HTTPS traffic, not raw database TCP connections. D. EBS multi-attach is limited to a single availability zone and does not provide multi-availability zone high availability. Managing the database on EC2 also drastically increases operational overhead compared to RDS. When an RDS requirement calls for high availability, automatic failover, and data redundancy within a single region, multi-availability zone deployment is the native, zero-downtime architectural choice. Question number 367. Scenario. A development team hosts its application source code in an external Git provider supported by AWS Code Connections. To enforce code quality, the team wants to run a suite of unit tests every time a pull request is created or updated. The process must display the success or failure status directly inside the pull request UI of the external Git provider. Additionally, the generated test output files must be archived into a designated Amazon S3 bucket for audit purposes. Which combination of configurations must a DevOps engineer implement to achieve this? Choose 3. More than one answer may be correct. Choices. Option A. Create an IAM service role that grants the testing service permissions to write to the designated S3 bucket and access the code connections connection. Option B. Provision an AWS code pipeline with a test stage. Configure an Amazon Event Bridge rule to trigger the pipeline specifically for pull request events. Option C. Create an AWS code build project. Configure a webhook within the project to trigger execution upon pull request creation and updates, and enable the build status reporting feature. Option D. Define an appspec.yml file in the repository root containing an artifacts phase to upload the generated test files to Amazon S3. Option E. Define a buildspec.yml file in the repository root that includes an artifacts section specifying the output files to be uploaded to Amazon S3. Option F. Configure an AWS Lambda function to pull the external Git provider for pull requests, invoke code build, and push the results back via the provider's API. The required selections are Option A. Create an IAM service role that grants the testing service permissions to write to the designated S3 bucket and access the code connections connection. Option C. Create an AWS code build project. Configure a webhook within the project to trigger execution upon pull request creation and updates, and enable the build status reporting feature. And Option E. Define a buildspec.yml file in the repository root that includes an artifacts section specifying the output files to be uploaded to Amazon S3. Here's why. AWS Code Build natively supports webhooks for external Git providers to trigger builds on specific events, such as pull request creation or updates. By enabling the Report Build Status option, Build Status Reporting, Code Build will automatically post a pass/fail badge back to the pull request in the external Git provider. Code Build uses a buildspec.yml file where the artifacts section defines which files should be uploaded to the configured S3 output location. Finally, the Code Build service role requires IAM permissions to interact with both the code connections connection and the destination S3 bucket. Now let's rule out the other options. B. AWS code pipeline does not natively trigger on pull requests. It triggers on merges to a tracked branch. Code Build webhooks are the correct mechanism for PR validation. D. appspec.yml is the configuration file used by AWS Code Deploy for deployments, not by Code Build for testing and artifact packaging. F. Using a custom AWS Lambda function to pull the Git provider and manage APs introduces heavy operational overhead and replaces a native feature that Code Build handles out of the box via webhooks. Keep this point in mind for the exam. For pull request, PR, validation, use AWS Code Build webhooks directly. Code pipeline is designed for continuous delivery after code is merged into the branch, not for testing transient PRs. Next up is question number 368. Consider this situation. A software engineering team is adopting semantic versioning for an internal application. They need an automated CI/CD pipeline that compiles the application code and assigns a semantic version tag to the resulting binary. The application heavily relies on numerous open-source packages from external package managers, and these dependencies must be cached securely to ensure reliable and fast builds. Which solution will satisfy these requirements using native AWS services? Choice A. Use AWS Code Deploy to package the semantic version of the binary and store the artifact on an Amazon Elastic file system, Amazon EFS, share. Choice B. Provision an AWS Code Artifact repository and configure it with an upstream connection to the external package managers. Create an AWS Code Build project to compile the code, authenticate with the Code Artifact repository, and publish the semantic version artifact. Choice C. Create an AWS Code Build project configured with build caching to pull dependencies directly from the internet. Publish the resulting semantic version binary to AWS artifact. Choice D. Set up an Amazon Event Bridge rule that triggers an AWS Lambda function to download external open-source packages. Configure AWS Code Deploy to compile the code and store the dependencies in an AWS Code Artifact repository. The best choice is option B. Provision an AWS Code Artifact repository and configure it with an upstream connection to the external package managers. Create an AWS Code Build project to compile the code, authenticate with the Code Artifact repository, and publish the semantic version artifact. This works because AWS Code Artifact is a fully managed artifact repository service that natively supports caching open-source packages by connecting to public upstream repositories like NPM, PyPI, Maven. AWS Code Build handles the compilation and semantic version generation, and it can authenticate securely via IAM to pull cache dependencies from Code Artifact and push the final compiled artifact back to Code Artifact for storage. AWS Code Deploy is an agent-based deployment service. It does not build code or manage artifact storage. EFS is a file system, not an artifact repository. AWS Artifact is a portal for downloading AWS compliance reports and security documents, not a software artifact repository for storing application binaries. AWS Code Deploy does not build code. Using Lambda to manually download and cache packages is highly inefficient and circumvents Code Artifact's native upstream caching capabilities. A helpful shortcut is this. Whenever a scenario requires managing, versioning, or caching open-source software libraries and internal binaries securely, AWS Code Artifact is the native solution. Next, question number 369. Scenario. An enterprise runs a public-facing legacy integration service on a single Amazon EC2 instance. The application stores state on an Amazon Elastic file system, Amazon EFS file system. Because of its architecture, the application cannot run concurrently on multiple active nodes and does not support a load balancer. A public Route 53 record currently points to an Elastic IP address on the primary instance. To reduce mean time to recovery, MTTR, a DevOps engineer provisions a warm standby EC2 instance attached to the same EFS file system and assigns the standby its own Elastic IP address. How should the DevOps engineer configure Route 53 to automatically redirect traffic to the standby instance when the primary instance becomes unhealthy? Option A. Provision an application load balancer, ALB. Update Route 53 to alias the ALB. Create target groups for each instance and attempt to direct all traffic to the primary target group. Option B. Change the Route 53 record to a failover routing policy. Configure the primary instance Elastic IP as the primary record and the standby instance Elastic IP as the secondary record. Associate health checks with the records so Route 53 returns the secondary record when the primary is unhealthy. Option C. Provision an application load balancer, ALB. Update Route 53 to alias the ALB and configure both instances as active targets. Option D. Use a weighted routing policy with weight 100 for the primary instance and weight 0 for the standby instance, but do not associate health checks with the records. In this case, choose option B. Change the Route 53 record to a failover routing policy. Configure the primary instance Elastic IP as the primary record and the standby instance Elastic IP as the secondary record. Associate health checks with the records so Route 53 returns the secondary record when the primary is unhealthy. Let's look at the reasoning. Route 53 failover routing is designed for active-passive DNS failover. The primary record is returned while its health check is healthy. When the primary becomes unhealthy, Route 53 returns the healthy secondary record. This preserves the single active instance requirement without introducing a load balancer. Let's quickly check the incorrect choices. A. The application explicitly does not support a load balancer, so introducing an ALB violates the workload constraint. C. This introduces an unsupported ALB and makes both instances active targets, which violates the requirement that only one node be active. D. Without health checks, Route 53 has no health signal that tells it to stop returning the primary weighted record after the instance fails. Exam tip. For a clear one primary/one standby DNS design, Route 53 failover routing is the native active-passive policy. Weighted 100 to 0 records can also participate in health-based failover when configured correctly, so health check details are decisive. Question number 370. The focus now shifts to artifact management. Here's what is happening. A DevOps team is configuring a continuous integration pipeline for a Java microservice using AWS Code Build. The Code Build project compiles the Java source code and generates a JR file as the output artifact. The team must store this artifact securely for subsequent deployment stages. How should the team configure the build environment to store the artifact? The choices are: Option A. Provision an Amazon Elastic file system, Amazon EFS, share. Define the EFS share as the artifact output location in the build spec.yml file. Attach an IAM policy to the code build service role granting EFS write access. Option B. Provision an Amazon S3 bucket. Configure the S3 bucket as the artifact output location in the code build project settings. Specify the files to include in the artifacts section of the build spec.yml file. Ensure the code build service role has permissions to write to the S3 bucket. Option C. Provision an Amazon S3 bucket. Configure the S3 bucket strictly within the build spec.yml file under the outputs mapping. Attach an S3 bucket policy allowing the code build project's resource access role to upload files. Option D. Provision an Amazon Elastic Block Store, Amazon EBS, volume. Define the EBS volume as the output destination in the code build project settings. Assign an IAM role to the volume allowing code build write operations. Go with option B. Provision an Amazon S3 bucket. Configure the S3 bucket as the artifact output location in the code build project settings. Specify the files to include in the artifacts section of the build spec.yml file. Ensure the code build service role has permissions to write to the S3 bucket. The main reason is AWS Code Build natively integrates with Amazon S3 to store build artifacts. The standard procedure requires specifying the target S3 bucket in the code build project configuration, the AWS console or CloudFormation definition, while detailing which specific files make up the artifact in the artifacts files section of the build spec.yml file. The code build service role must be granted S3. Put object permissions to successfully write the artifacts. The other choices do not work because while code build can mount EFS for shared caching, S3 is the native, durable, and standard artifact store for CI/CD pipelines, integrating seamlessly with code pipeline. C. The S3 destination bucket is defined in the code build project settings or code pipeline stage, not directly inside the build spec.yml outputs mapping. Furthermore, code build uses a service role, not a resource access role. D. Code build runs in managed compute environments. You cannot attach a standalone EBS volume as an artifact output destination in the project settings. The main takeaway is in code build, the build spec.yml dictates what files make up the artifact, but the code build project configuration dictates where the artifact is stored, typically an S3 bucket. Here comes question number 371. A corporation manages multiple workload accounts in an AWS organization's OU. The OU currently has an SCP that allows all actions. The company standardizes infrastructure as code in GitHub and uses AWS code connections with AWS CloudFormation Git Sync. Developers will deploy and automatically synchronize CloudFormation stacks from the GitHub repositories in multiple AWS regions. Security requires developers to create connections only for the approved GitHub provider. Which 3 actions should the DevOps team take? Select 3 answers that satisfy the requirement. Review the options. Option A. Attach an SCP to the OU that denies code connections. Create connection when the code connections. Provider type condition key does not equal GitHub. Option B. Attach an SCP to the OU that explicitly allows code connections. Create connection only when the code connections. Provider type condition key equals GitHub, while leaving the existing full AWS access SCP attached. Option C. Create one AWS code connections connection to GitHub and reuse that connection in all operating AWS regions. Option D. Create a separate AWS code connections connection in every operating region because connection resources are regional. Option E. In each region that contains a target CloudFormation stack, create the repository link and sync configuration that use the global connection and configure CloudFormation Git Sync for the repository. Option F. Create an AWS code pipeline in every region that uses AWS code commit as the source and deploys the CloudFormation stacks. The answers that work here are Option A. Attach an SCP to the OU that denies code connections. Create connection when the code connections. Provider type condition key does not equal GitHub. Option C. Create one AWS code connections connection to GitHub and reuse that connection in all operating AWS regions. And Option E. In each region that contains a target CloudFormation stack, create the repository link and sync configuration that use the global connection and configure CloudFormation Git sync for the repository. This is the best choice because option A creates an enforceable guardrail because an explicit deny in an SCP overrides permissions otherwise allowed by full AWS access, and the current code connections service prefix and provider condition key are code connections. Option C is required because code connections connection resources are global and need to be created only once for use in other regions. Option E completes CloudFormation Git sync by creating the repository link and sync configuration resources for the regional CloudFormation targets while reusing the global connection. Here's why the alternatives are not suitable. B. With full AWS access still attached at the same scope, an additional allow statement does not create the required restriction. An explicit deny guardrail is needed. D. Code connections are global resources and are replicated across regions, so separate connection resources are unnecessary. F. The requirement is to sync from GitHub through code connections and CloudFormation Git sync. Replacing the source with code commit changes the stated source control architecture and adds an unnecessary pipeline. Here's a useful exam tip. AWS code connections are global resources. For governance, use the current code connections IAM service prefix and an explicit deny SCP when full AWS access remains attached. Question number 372. We're moving on to CI/CD pipelines. An enterprise maintains two AWS accounts, a build account managing an AWS code pipeline and a deploy account managing the production workloads. Code pipeline in the build account uses the pipeline_role IAM role and drops a compiled application artifact into an Amazon S3 bucket within the build account. The artifact is encrypted using a customer-managed AWS KMS key located in the build account. To facilitate deployment, an AWS code deploy application runs in the deploy account. A DevOps engineer has already updated the KMS key policy to permit access from the deploy account. The engineer also created a deploy_role in the deploy account with permissions for code deploy operations and attached an IAM role to the EC2 instances in the deploy account granting access to the S3 bucket and KMS key. Which additional configurations are necessary to successfully deploy the artifact across the accounts? Choices. Option A. Update the S3 bucket policy in the build account to grant read access to the deploy account. Configure the deploy_role trust policy to allow the deploy account to assume it. Add a policy to pipeline_role, allowing it to assume the deploy_role. Option B. Update the S3 bucket policy in the build account to grant read access to the build account. Configure the deploy_role trust policy to allow the deploy account to assume it. Add a policy to the EC2 instance role, allowing it to assume pipeline_role. Option C. Update the S3 bucket policy in the build account to grant read access to the deploy account. Configure the deploy_role trust policy in the deploy account to allow the build account to assume it. Add a policy to the pipeline_role, allowing it to assume deploy_role. Option D. Update the S3 bucket policy in the build account to grant read access to the deploy account. Configure the deploy_role trust policy to allow the build account to assume it. Add a policy to the deploy_role, allowing it to assume the pipeline_role. The right response is option C. Update the S3 bucket policy in the build account to grant read access to the deploy account. Configure the deploy_role trust policy in the deploy account to allow the build account to assume it. Add a policy to the pipeline_role, allowing it to assume deploy_role. For a cross-account code pipeline deployment, 3 security boundaries must align. First, the S3 bucket in the build account needs a bucket policy explicitly granting access to the EC2 instances and roles in the deploy account. Second, the code pipeline orchestrator, pipeline_role, in the build account must assume the target deployment role, deploy_role, in the deploy account to trigger code deploy. This requires the deploy_role trust policy to trust the build account and the pipeline_role identity policy to have STS. Assume role permissions targeting the deploy_role. The remaining options can be eliminated because A. The trust policy for deploy_role must allow the build account, specifically pipeline_role, to assume it, not the deploy account itself. B. S3 bucket policies implicitly allow the owning account. The policy must grant access to the deploy account. Furthermore, the EC2 instance does not assume the pipeline_role. D. The deploy_role does not assume the pipeline_role. The pipeline orchestrator, pipeline_role reaches out to assume the deploy_role. In cross-account pipeline architectures, the pipeline's execution role must always assume a cross-account role in the target deployment account. Both sides of the IAM trust relationship, the assume role policy on the pipeline and the trust policy on the target role, must be configured along with cross-account KMS and S3 policies. Question number 373. Let's go. A DevOps team uses AWS code pipeline to orchestrate the continuous delivery of a microservices architecture. To ensure the application can handle unexpected infrastructure failures, the team designed an AWS fault injection service, AWS FIS, experiment template that terminates random EC2 instances. The team wants to automatically execute this chaos engineering experiment as a validation step within code pipeline immediately after the staging deployment. How should the DevOps team integrate the AWS FIS experiment into the pipeline? Option A. Export the AWS FIS experiment template to an S3 bucket. Add a code build test action to the pipeline that executes an AWS CLI script to start the experiment. Grant the code build service role permissions to execute FIS experiments. Option B. Add an AWS Lambda action to the pipeline. Write a Lambda function utilizing the AWS SDK to trigger the FIS experiment and poll for its completion. Grant the Lambda execution role permissions to start FIS experiments. Option C. Add an AWS FIS action to a new stage in code pipeline. Configure the action to target the ID of the AWS FIS experiment template. Ensure the code pipeline service role has permissions to start the experiment. Option D. Define an Amazon Event Bridge scheduled rule triggered by a pipeline state change. Grant the rule permissions to start the AWS FIS experiment. Configure the pipeline to wait for an external webhook from Event Bridge. The answer here is option C. Add an AWS FIS action to a new stage in code pipeline. Configure the action to target the ID of the AWS FIS experiment template. Ensure the code pipeline service role has permissions to start the experiment. Here's why. AWS Code Pipeline natively supports AWS Fault Injection Service, FIS, as an action provider. You can add a test stage and select AWS FIS as the action type, supplying the experiment template ID. This eliminates the need for custom scripts, Lambda functions, or complex polling mechanisms. The code pipeline service role simply needs the required IAM permissions, FIS, start experiment, to trigger the action. Now let's rule out the other options. A. Using code build to run an AWS CLI script introduces unnecessary compute overhead and maintenance when a native FIS action type exists in code pipeline. B. While an AWS Lambda function can orchestrate the experiment, it requires custom code to trigger the experiment, manage state, and poll for results, violating the principle of using native integrations. D. Event Bridge is an event router and scheduler. Detaching the test execution from the pipeline flow and relying on webhooks creates a fragile, overly complex asynchronous workflow. Keep this point in mind for the exam. AWS Code Pipeline includes native action integrations for many AWS testing and security tools like AWS FIS, CodeGuru, and Device Farm. Always choose the native action type over custom code build scripts or Lambda functions when available. You have completed set 20 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.